Okay, so just finishing off simple harmonic motion. This is just a little bit of information reminding us about phasors. So our reference circle lets us solve problems involving time and displacement. What we now want to look at is, can we solve some problems involving velocity and acceleration? So we've already seen this idea of the reference circle before. So we can have something going vertically or moving horizontally. Okay. Now if we think we know that the radius is going to be the same as the amplitude. Now this little thing moving around our reference circle is going to have a velocity. Okay. Now if we've got an object moving at constant speed in a circle, our velocity is going to be given by r times w. Okay. Now we also know that when an object's moving at constant speed in a circle, it has got some acceleration, and that's centripetal acceleration. And if we remember back, our centripetal acceleration will be given to us by v squared over r. Now if we substitute those things in, we substitute the fact that our r here is going to be capital A, because it's going to be our amplitude, then we end up with a expression for acceleration of a, okay, because phasors we're going to help to explain where some of these equations that we use for velocity and acceleration are going to come from. So remembering then that our little particle is going to go around our reference circle in an anti-clockwise direction. As it does that, this I guess this sort of direction that we're looking at here, this phasor in the middle, is also going to rotate around. So this vector that we've got here is going to rotate around. So our velocity and acceleration phasors of the reference circle particle can be put into their own reference circles. Each vector is going to be rotating about the centre of the circle, but they're all going to be slightly offset because you know, when you've got simple harmonic motion, we've got maximum velocity, maximum acceleration at different parts of your simple harmonic motion. Okay, so we'll first of all start with our displacement phasor. So we'll look at something. So as it moves up vertically, okay, for a distance y, we're going to have this little phasor here. So it's going to have moved through this angle theta here. Okay, now we can also hopefully remember that theta is equal to wt. Okay, so at time 0 it's here, at time equals t it's up here. Okay, so it's time equals t up here. So if we want to write an expression for y, if we think back to the last video and what we did, we can see that y is equal to a sine wt, because remember we said that sine wt was going to be y divided by a, and here theta is wt, and we replace that. Okay, so this is our phasor for displacement. And we can use this equation here to work out what that displacement would be. We know the amplitude, we know the angle that it's turned through, or in fact we've been able to work out our angular velocity, and we know what time we've used in the question. So again, yeah, any of these things we could put these in to look at our displacement. Now when we're looking at a velocity phasor, okay, our velocity is going to be out of phase with our displacement, and we've looked at that also before. Excuse me. So I'll try and fit this on the same diagram. So now we're looking at velocity here rather than displacement. So we'll look at the velocity that we're travelling at here. Okay. Again, we're going to have moved through an angle. Okay, we'll look over here. Okay, this will be our velocity vector. Okay. Now we've said already that velocity is RW. Okay. So we're going to be looking at this now as velocity. RW is also going to be the same as AW. Okay, because we know that our radius here is the same as the amplitude. And again, going to move through an angle of theta, and theta is equal to WT. So if we're going to write an expression this time, we are going to be looking at velocity. Excuse me. And we get to this equation here. Those of you, like I said before, who've done some calculus will know that if we differentiate sine, we get this expression here. Okay, so this is just differentiating. Okay. Now moving on from that, we've also got acceleration to think about. So I'm going to go down here with our acceleration phasor. Okay, acceleration AW squared. Okay, so this is our acceleration vector. Again, we're going to have moved 3 theta degrees. And again, this expression comes from differentiation. Okay, here's our acceleration vector, okay, size of our acceleration, and then we're differentiating our cosine term. And also in your notes you would have seen that we've drawn the graphs of the phasors and how the phasors change. You would have seen how those graphs also relate to the movement of the phasors. Really vital always to remember that your phasors always go around in an anti-clockwise direction. So you just have to be a little bit careful with these phasor diagrams. These ones are looking at moving from the equilibrium position. Okay, so displacement is going to be y. The time taken for our particle to go from the equilibrium position to a certain displacement y. Okay, so these 3 equations are only valid if t equals 0 at the equilibrium position. Okay, so these 3 here only if t equals 0 at equilibrium. Sometimes in a question it will be more advantageous, or you'll be specifically asked to start at one of the endpoints. Okay, so when we're looking at the end position and we go through this, our vectors are going to be in slightly different positions, so they all have moved around slightly. So our displacement vector will be in this direction, our velocity vector in this direction, and our acceleration vector now will be over here. And that gives us 3 new equations to use when we're looking at it starting at our end position. I'm not going to draw all of those on there, and like I say, we've been through it in your notes. But if you're t equals 0 at an end point, so either at the top or at the bottom, we end up with the equations y equals a cos wt, because we're around here, v equals minus a w sine wt, and a is equal to minus a w squared cos wt. Now there are a couple of special cases of these. We can also get this equation as well. Okay, and that's by combining equations for y and a, we get this equation for acceleration as well. And this is back to the equation that helps us to define if something is simple harmonic motion. The other thing just to be aware of is there's also those special cases where you've got things being at a maximum. Okay, and if you think about the angles, these equations simplify right down to just these parts at the beginning. So y equals a, b equals aw, and a equals minus awt. So have a look at your special cases as well when these things are a maximum. And that basically covers phasors. I'll put up some videos also where we go through some of the assignment questions, so you can see these equations and phasors being used in questions if you're still struggling with those.